Hi students, welcome to my YouTube channel Lokesh Gupta Chemistry Classes. Today in this video I want to discuss some objective questions on the ionization energy, electron affinity and electronegativity. Now before going to discuss the objective questions, I want to explain some concept also. See, from the gaseous atom M, to remove electron and convert it into M plus gas, energy required is called ionization energy of M. It is the ionization energy of M. Now reverse this equation means what? To the M plus gas, when an electron is added, M gas formed plus energy released. Now here we added electron, this released energy is the electron affinity of this M plus gas. Here absorbed energy, here released energy, both are equal in magnitude. But it is positive value. Absorbed na, it is released energy na negative value. So from this, what is the conclusion? Ionization energy of M gas is numerically equal to electron affinity of M plus gas. In the ionization of M gas, product is M plus gas na? That product M plus gas electron affinity, reactant M gas ionization energy, both are equal. Next, now to the gaseous atom, when an electron is added, X minus formed plus some energy released. Now this released energy is the electron affinity of X. Electron affinity of X. Now reverse this equation. Now it means what? From the X minus gas, to remove electron and convert it into the X gas, some energy required. Now this required energy is called ionization energy of X minus gas. Now this released energy, this absorbed energy, both are numerically equal. So from these two equations, what is the conclusion? Electron affinity of X is numerically equal to ionization energy of X minus. In the electron affinity of X, what is the product? X minus na. That product ionization energy is numerically equal. So electron affinity of X gas is numerically equal to ionization energy of X minus gas. This one, numerically equal. Next, one more point. For any element, electron affinity value possible, ionization energy value possible. Which one is more? Means for an atom, isolated gaseous atom, when an electron is added, some energy is released. That is the electron affinity. From the same gaseous isolated atom, when an electron is removed, some energy required. That is ionization energy. Numerically, which value is more? For any element, ionization energy value is more than its electron affinity. Means from an isolated gaseous atom, to remove one electron, more energy required when compared with the energy released when an electron is added. So for any element, ionization energy value is more than its electron affinity value numerically. For example, you take the chlorine. For this ionization energy, means to remove one electron from the isolated gaseous chlorine atom, 1254.8 kilojoules energy per mole required. But when an electron is added to isolated gaseous neutral atoms of chlorine, then 348 kilojoules only will be released per mole. So which value is more? For any element, ionization energy value is more than its electron affinity. And one more point, among all the elements, electron affinity highest for chlorine. How much? Minus 348 kilojoules per mole. Next, among all the elements in the modern periodic table, ionization energy least for 1A group last element cesium. That one how much? 375 kilojoules per mole. Now see, by comparing these two values, what we can say? See, among all the elements, ionization energy least for cesium. When compared with this value, among all the elements, electron affinity highest for chlorine. that chlorine electron affinity value only less. So from this, what is the conclusion? Electron affinities of all elements in the modern periodic table is less than that of ionization energy of any element in the modern periodic table. Electron affinity of all the elements in the modern periodic table is less than that of ionization energy of any element in the modern periodic table. So these are some important points. Now let me start the objective questions. First question. Among the following, from which one energy released is maximum when an electron is added? When an electron is added, from which one energy released is maximum? Fluorine, chlorine, bromine, cesium plus. See, fluorine, chlorine, bromine. Energy released when an electron is added means electron affinity. We know among the halogens, electron affinity highest for chlorine. So among these three, when electron is added to the chlorine, energy released maximum. Now in between these two, see, to the Cs plus, electron added, energy released is what? Electron affinity of Cs plus. Just now we discussed electron affinity of M plus numerically equal to ionization energy of M gas. So to the Cs plus, when an electron is added, energy released is equal to ionization energy of cesium. Just now we discussed ionization energy of any element more than that of electron affinities of all the elements in the modern periodic table. So to this chlorine atom, when electron is added, 348 kilojoules will release. Now to this Cs plus, when an electron is added, energy released equal to ionization energy of cesium. So in this case, 375 kilojoules energy will be released. So answer is Cs plus. Next. To this, when electron is added, energy released is maximum. Boron plus, carbon plus, nitrogen plus, Cs plus. See, energy released when an electron added means electron affinity. Electron affinity of M plus is numerically equal to ionization energy of M. So we have to know the ionization energy order of these elements. We know boron, carbon, nitrogen, oxygen. In periods left to right side, ionization energy increases. But ionization energy of nitrogen more than that of oxygen. Why? Nitrogen has half-filled 2p subshell stable electronic configuration due to that reason. So among these four elements, to remove electron from the nitrogen, maximum energy is required. Now, from this to this monoatomic ions, when electron is added, in which case energy release will be maximum? Nitrogen plus. It is based on which concept? Electron affinity of M plus gas is numerically equal to ionization energy of M gas. So among boron, carbon, nitrogen, oxygen, ionization energy highest for nitrogen. To remove electron from nitrogen atom, more energy required. Then unipositive ions formula. Now when electron is added to B plus, C plus, N plus, O plus, energy release will be maximum for N plus. Next. Among the following, how many first electron affinity orders are correct? See, 7th A group, chlorine greater than, fluorine greater than, bromine greater than, iodine. See, in the S and P blocks, except in 1A group, electron affinity of the first element is less than that of second element. See, down the group electron affinity decreases. So electron affinity should be highest for the first element. But except in 1A group, in the remaining groups of the S and P block, electron affinity of the first element should be highest, but not correct. Electron affinity of the first element less than that of second element. In 7th A group, electron affinity of fluorine is less than that of chlorine. Why? Due to the small size of fluorine. Now in this 7th A group, fluorine electron affinity just less than that of chlorine. So this is correct. But in 6th group, electron affinity of oxygen not only less than that of sulfur, it is least among the 6th group. Least among the 6th group. It is also correct. Next, now if you compare fluorine, chlorine, chlorine more. If you compare oxygen, sulfur, sulfur more. When compared with this 6th group elements, for this 7th group elements only electron affinity more. So overall this order is also correct. Now come to this one. Just now we discussed that exception is not observed in the 1A group. Why? Because see, why electron affinity of fluorine less than that of chlorine? Fluorine is smaller in size than the chlorine. In the fluorine valency shell, 7 electrons are there. In the fluorine valency shell, 7 electrons. In the chlorine valency shell also, 7 electrons are there. So now, but here 7 electrons in the small volume. Here 7 electrons in big volume. So here electrons density more in fluorine. Here in chlorine, relatively electrons density less. So in between the already existed electrons of fluorine and incoming electron, little bit more repulsion. Here also repulsions are there, but here little bit more repulsion in between the already existed electrons and the electron what we are going to add. So now some of the energy which is going to be released is utilized to overcome these repulsions. So finally energy released is less for fluorine than that of chlorine. But see, in case of 1A group, in their valence shell, one electron only. So this electron density, this one not affecting a lot, only 1 electron. So that's why in this 1A group, no exception. Electron affinity of hydrogen more than that of lithium, lithium more than that of sodium. So this one correct only. This concept recently given in 2020 January spell mains exams also. Next, now what about this one? Phosphorus, silicon, sulfur, chlorine. What is the electron affinity order? See, silicon, phosphorus, sulfur, chlorine. In the periods from left to right side, electron affinity increases. So we are expecting that electron affinity should be least for silicon, but here phosphorus has 3p3 stable half p subshell electronic configuration. If it gains electron, it will lose its stability. That's why for this electron affinity is less. Actually, in case of noble gases, helium, neon, argon, krypton, xenon, they have stable electronic configuration. If they gain electron, they lose their stability. That's why for those elements, electron affinity E1 is not exothermic, endothermic. Next, similarly, for nitrogen also endothermic. Beryllium, magnesium also endothermic. But in case of phosphorus, stable electronic configuration. For this electron affinity is not endothermic, exothermic only, but energy released is less. So electron affinity of beryllium, magnesium, nitrogen and noble gases is endothermic. Phosphorus just less negative. So from silicon to phosphorus, electron affinity decreased. So electron affinity order, phosphorus less than, silicon less than, sulfur less than, chlorine. So this one also correct, first electron affinity order only. So silicon more than that of phosphorus. Phosphorus only less because of stable electronic configuration. Next, come to another one. Among the following, formation of which one from its atom is exothermic? Formation of which one from its atom is exothermic? See, O2 minus gas, that is oxide ion. Formation of O2 minus gas from oxygen atom, is it exothermic? See, first to this O gas, we have to add one electron. Then O minus gas you will get. It is first electron affinity, exothermic only. Next, to this we have to add one more electron. Then O2 minus gas you will get. Now it is second electron affinity. Second electron affinity is endothermic. And one more point, when compared with the first step, in the second step, energy absorbed is more. When compared with the energy released in the first E.E.A. first electron affinity, energy absorbed in the second electron affinity is more positive, more for majority of, for almost all elements. So less negative plus more positive, overall positive means endothermic. So formation of oxide ion from oxygen gas, endothermic. Sulfide ion, here also, sulfur gas plus 1 electron, S minus gas, electron affinity. To the S minus gas, we have to add one more electron, S2 minus gas, second electron affinity. First electron affinity, exothermic. Second electron affinity, more endothermic. So formation of this one also, endothermic only. But our question is exothermic. Our question is exothermic. Next, formation of hydride ion H minus, H gas plus 1 electron, it gives rise to H minus gas. So E1 only. So that's why formation of hydride ion, gaseous hydride ion from gaseous hydrogen atom is exothermic. What about formation of the cupric ion? Formation of the cupric ion. Copper gas, it gives rise to Cu plus gas plus electron, IP1. Cu plus gas, it gives rise to Cu2 plus gas plus electron. Second electron we have to remove. So it is IP1 plus IP2. IP values endothermic. So it is also endothermic. So formation of hydride gaseous ion from hydrogen atoms is exothermic. Next, among the following, electronegativity highest for. Electronegativity now. Electronegativity highest for hydrogen, deuterium, tritium. Hydrogen, deuterium, tritium. See, isotopes of the hydrogen. For isotopes, electronegativity, is it equal? No. Slightly, not to the greater extent, slightly it will change. In case of hydrogen, in all these one electron only. In case of hydrogen, one proton. In case of deuterium, in the nucleus, neutron is also there. So here only positively charged proton, here neutron also. So that's why little bit electrons attracting tendency, little bit, very little bit only decreases. Next, tritium, here in the nucleus, one more extra neutral atom, neutron added. So that's why electrons attracting tendency, very, very little bit only decreases. So electronegativity more for hydrogen. So electronegativity order, hydrogen greater than, or you can call it as protium, greater than deuterium, greater than tritium. It is the electronegativity order. Next, iron Fe2 plus Fe3 plus. For which one electronegativity is highest? Electronegativity, the tendency to attract the bonding electron pair. See, iron atomic number 26. Here 26 electrons, 26 protons. But Fe2 plus, see, how many electrons? 26 minus 2, 24 electrons, but protons 26. Iron 3 plus, if you remove 3 electrons from iron, you will get iron 3 plus. So now 23 electrons, but protons, 26 protons. So from here to here, electrons decreasing. So bonding electron pair attracting tendency also increases. So electronegativity highest for this one. Iron less than, iron 2 plus less than, iron 3 plus. Now in the same style, now answer this one. Chlorine atom, Cl plus, Cl minus. Chlorine atomic number 17. Here 17 electrons, 17 protons. But here 18 electrons, 17 protons. Here 16 electrons only, 17 protons. So here attraction more. So here for this ionization energy, electronegativity more. Next, this one. Among this electronegativity highest for sp2 hybridized carbon, sp hybridized carbon, sp2 hybridized nitrogen, sp hybridized nitrogen. See, with increasing the percentage of s character of hybrid orbital, electronegativity of the hybrid orbital increases. For sp3 hybrid orbital, 25% is s character. For sp2, 33.3% is s character. For sp hybrid orbital, 50% is s character. So for which one s character is more? sp hybrid orbital. With increasing the percentage of s character of the hybrid orbital, electronegativity will increase. So in between these two, for this carbon electronegativity more. Why? Here 33.3% is s character. Here 50% is s character. So that's why in between these two, this one. In between these two, this one. Now in between these two, from carbon to nitrogen, electronegativity increase now. So this one. For this electronegativity highest. See, sp3 hybridized carbon, sp hybridized carbon triple bond C. Similarly, sp hybridized nitrogen. In cyanide, this nitrogen is sp. See, for carbon compounds, to find the hybridization, one simple rule, finger rule is there. Carbon valency 4, open 4 fingers. Now, how many fingers we have to close? That is equal to number of pi bonds formed by that carbon. If a carbon not forming any pi bonds, don't close any finger, then sp3 hybridization. If a carbon forming one pi bond, close one finger, then sp2 hybridization. If a carbon forming two pi bonds, close two fingers, then sp hybridization. So this carbon, sp hybridized carbon. For this nitrogen also, this rule applicable. It is forming two pi bonds now, sp hybridized nitrogen. So it is the answer. sp hybridized nitrogen is among these most electronegativity. Next, one more question. In which of the following process, energy released means among the following which are exothermic, which process is or exothermic? First one, Na plus gas plus electron, it gives rise to Na gas. Is it exothermic? See, this reverse one is ionization of sodium. This reverse process, ionization endothermic. Now this one, for the endothermic process, reverse one exothermic. It is endothermic. So now that's why it is exothermic. So it is exothermic only. Next, B, Na plus gas, it gives rise to Na2 plus gas plus electron. Now what is this? Second ionization energy of sodium. IP1, IP2, IP3, everything are endothermic only. So it is endothermic. See, electron affinity, E.A.1 is exothermic, except for beryllium, magnesium, nitrogen, noble gases. Electron affinity of beryllium, magnesium, nitrogen, noble gases are endothermic. Remaining electron affinities, remaining elements E.A.1 exothermic. Next, E.A.2, E.A.3, E.A.4 and so on. These are all also endothermic. Next, nitrogen gas plus electron, it gives rise to N minus gas. Now to the nitrogen gas we added electron. So it is the first electron affinity of nitrogen. It is not exothermic. For beryllium, magnesium, nitrogen, noble gases, first electron affinity is endothermic. So it is not endothermic. Next, He minus gas, it gives rise to He gas plus electron. See, this reverse one, to the helium addition of electron to form helium minus, it is first electron affinity of helium. First electron affinity of helium endothermic. Now reverse reaction for the Endothermic reaction, reverse reaction, exothermic. Now, from the helium minus gas, if you remove the electron, then energy will be released. So it is the exothermic one. It is the exothermic process. Next. M2 plus gas plus electron, it gives rise to Mg plus gas. Is it exothermic or endothermic? See, this reverse one, IP2 of magnesium. IP2 endothermic. It is endothermic now. Now this one exothermic. So like this, they may give the questions for JEE mains and JEE advanced. So these are the some objective questions on ionization energy, electron affinity and electronegativity. If you like this video, please subscribe my channel and click on the bell icon to get all my notifications. Okay, bye students. We will meet again with another good concept.